Welcome to The Explainer, everyone. Let's just jump right in, because today we're unpacking a massive conceptual leap in quantum hardware design. We're going to see how a super simple metaphor, an ant crawling on a surface, literally helps us visualize and solve the wildly complex mechanics of two-dimensional quantum computing. We're essentially taking the theoretical physics of quantum dots and translating them into a mapped-out visual landscape. And why does this matter? Well, mastering this terrain is absolutely crucial for unlocking the stable, error-free quantum computers of the future. Picture an ant living its whole life on a flat 2D plane. From its perspective, it's just dealing with simple left, right, forward, and backward movements. But in reality, the path it takes, like where water pulls up or where it's actually safe to walk, is completely dictated by a hidden vertical dimension. There's this whole 3D landscape of hills and valleys underneath it. Believe it or not, our quantum hardware works the exact same way. The dials we control on the surface are actually ruled by a vast hidden landscape just beneath. So here's our roadmap for this explainer. We'll start with that 2E quantum ant metaphor, map out the singlet-triplet energy landscapes, explore the sweet spot valley, look at the valley tracking control model, and finally wrap it all up with the 5-layer quantum architecture. All right, section 1, the 2D quantum ant. Let's really unpack this foundational metaphor. Think about what that ant actually experiences versus what it doesn't. In our quantum setup, the x and y coordinates are basically our control knobs, stuff like gate voltage and magnetic fields. You know, the dials we're physically turning in the lab. But what the qubit actually experiences is the z height, which is the hidden potential energy. Just like that ant instinctively seeks the lowest, safest path through a physical valley to avoid getting blown away, a robust qubit has to follow the valleys of this hidden energy landscape to survive environmental noise. Moving on to section 2, singlet-triplet energy landscapes. Let's map out what this hidden terrain actually looks like. Now, what's incredibly cool here is how these quantum states emerge as distinct 3D surfaces. When we put two electrons into a double quantum dot, they interact and form specific spin states, what we call the singlet and triplet states. What you're seeing here is us mapping the energy of those specific states against our control coordinates, so the magnetic field and gate voltage. This isn't just some abstract math on a chalkboard. This is the literal physical topography our quantum states live in. Let's break down this blueprint. That green surface, that's the singlet energy state, and the yellow one is the triplet energy state. Notice how they slope right toward each other. But where they meet, they don't just crash. Thanks to some really complex coupling effects, they create an avoided crossing. It's kind of like two magnets repelling each other right before they touch, which bends the landscape to form that bright blue line right down the middle. That line is the sweet spot valley. It's this critical, protected path where our qubit's frequency is stable and errors are practically zero. So here's the absolute game changer. We have to fundamentally rethink quantum computing. A qubit isn't just some fragile, static dot sitting still in space. Not at all. It is a dynamic state-space traveler. We have to view it as a protected, two-level subspace that we actively navigate along these topological valleys. That brings us to section 3, the sweet spot valley. Let's dive a bit deeper into how we navigate that path. You see, a sweet spot isn't just one magic coordinate where everything is perfect. Real-world quantum noise has direction and magnitude, so a true sweet spot valley is a continuous route. Think of it like a protective trench. Perpendicular to the trench, the walls are flat against random noise, which shields the qubit. But along the actual path of the trench, the way forward is perfectly open for us to execute our intentional control operations. And this completely illustrates how we scale the whole concept. On the left, you've got a single qubit successfully navigating its protected valley. But look at the right side. A good valley isn't just an isolated path, it can be designed as an interconnected network. By hooking up different valleys, we can actually route our qubit between entirely different quantum functions. We can link a sensing valley to a communication valley and then over to a computing and readout valley. This network is the whole shebang. It's what lets a quantum computer actually run complex algorithms without the qubit ever leaving the safety of that trench. All right, section 4, the valley tracking control model. How exactly do we drive through this network? So how do we move a qubit without destroying it? This is quite literally the million-dollar question in quantum mechanics. We know the valley is there, but if we push the qubit the wrong way, or if some random environmental interference knocks it off course, poof, the quantum state collapses. This is exactly why we need to contrast two very different kinds of movement. First up, you have uncontrolled drift. This is our worst enemy. It's random, destructive movement caused by fluctuating temperatures, charge noise, you name it. It just knocks the qubit right out of the valley. But then we have our hero, guided valley tracking. This is our active, real-time control model. It continuously adjusts the parameters to keep the qubit intentionally and safely routed right down the center line of the valley, completely dodging the noise. But actually driving this route is an incredibly delicate balancing act, something we call the adiabatic route. See, you have to drive the qubit through the valley fast enough so it doesn't just sit there and succumb to environmental decoherence over time. But if you move it too fast, you trigger what are called Landau-Zener transitions. Basically, the qubit crashes right out of its protected state just because it was going too fast. It's exactly like driving a race car. You need the absolute perfect speed to hug the corners of the valley without spinning out. Section 5, 5-layer quantum architecture. Let's zoom out and see how this whole ecosystem scales up. Let's take a look at this architecture and see how it builds from the ground up. Down at the base, we have the physical layer. These are the actual quantum dots sitting on our 2D chip. Right above that is the landscape layer, which is that hidden 3D energy height map we've been talking about. Then comes the noise layer. You can think of this like the weather. It basically determines how wide or narrow our safe valley is on any given day. On top of that is the route layer, where our valley tracker actively pilots the qubit. And finally, sitting all the way at the top is the logical layer, where we actually pull off our error-tolerant quantum computing and sensing. So if you were the one operating this revolutionary machine, here is your real-time 5-step blueprint. 1. You map the energy landscape using spectroscopy. 2. You measure the current environmental noise. 3. You mathematically extract the absolute optimal sweet spot valley. 4. You track your adiabatic route, keeping your speed perfectly balanced. And 5. Once you're safely positioned, you execute your quantum function. And that brings us beautifully back to where we started. Because mastering quantum computing isn't just about throwing better hardware dots onto a 2D surface. It's really about mastering this topographical journey. The quantum processor of the future is, essentially, a highly complex route planner, constantly guiding states through an invisible landscape. I want to share this exact framing from the source material with you all because it just perfectly captures this entire paradigm shift. A future qubit survives and computes by following the hidden sweet spot valley of its energy landscape. Just like our 2D ant survives the elements by finding the lowest trench, our quantum information survives by continuously walking that optimal path. It really makes you think, doesn't it? We're essentially becoming cartographers of a microscopic, multidimensional world. As we get better and better at mapping and navigating these hidden 3D topographies in real time, what entirely new quantum horizons are we going to navigate next? The possibilities for sensing, networking, and computing are just wide open right now. Thank you so much for joining me on this journey through the quantum landscape in today's Explainer. Stay curious and keep exploring.